Our local supercluster, a sprawling collection of thousands of galaxies stretching across 110 million light-years of space, represents the absolute limit of cosmic architecture. The largest scale at which matter can organize itself into coherent structures before the fundamental forces of cosmic expansion tear everything apart forever. But here's what makes this absolutely mind-bending. Superclusters like ours contain enough gravitating mass to collapse into single, unimaginably massive black holes within a few billion years. The gravitational forces involved are stupendous. We're talking about the combined gravitational attraction of hundreds of trillions of stars, countless black holes, and vast reservoirs of dark matter, all pulling inward with forces that should compress these structures into cosmic-scale catastrophes. Yet superclusters never collapse. They remain stable, sprawling, magnificent architectures of matter that persist for billions of years without ever succumbing to their own gravity. This creates one of the most profound mysteries in modern cosmology. If gravity always wins on small scales, collapsing gas clouds into stars into neutron stars and black holes and star systems into galactic cores, why does gravity suddenly become powerless at the largest scales? What invisible force counteracts gravitational collapse when we zoom out to supercluster dimensions? Here's what makes this paradox truly extraordinary. The same gravitational forces that are powerful enough to merge entire galaxies, creating spectacular cosmic collisions, like the ongoing merger between the Milky Way and Andromeda, somehow become completely impotent when operating across the 100 million light-year scales that define supercluster architecture. We are witnessing a fundamental transition in how the universe organizes matter, a cosmic phase change where gravity shifts from being the dominant organizing force to being completely overwhelmed by something else. The numbers involved are staggering beyond comprehension. Our local supercluster contains approximately 1,015 solar masses worth of ordinary matter, plus roughly 5 times more in dark matter. If this mass were to collapse under its own gravity, it would create a black hole with an event horizon spanning several light-years larger than the orbit of Proxima Centauri. The gravitational time dilation near such an object would be so extreme that time would essentially stop relative to the external universe. Yet none of this happens. Instead of collapsing, superclusters are actually expanding, with their component galaxies moving apart from each other at velocities that increase with distance. The Hubble limiter law V equals HDD governs this expansion, but the physics underlying why this expansion overwhelms gravity at supercluster scales while remaining irrelevant at galactic scales represents one of the deepest unsolved problems in cosmology. You need to understand something profound about what we're exploring tonight. This isn't just another astronomy question about distant cosmic structures. The stability of superclusters versus their theoretical gravitational collapse represents a fundamental test of our understanding of gravity, dark matter, dark energy, and the ultimate fate of the universe itself. The answer determines whether cosmic structure formation represents an ongoing process or whether we are witnessing the last generation of large-scale structures before cosmic expansion tears everything apart. Recent observations from the Dark Energy Survey and the Euclid Space Telescope have revealed that supercluster formation and evolution operate according to principles that challenge our basic understanding of how gravity works on cosmic scales. These massive structures exhibit dynamics that seem to violate the inverse square law of gravitational attraction, suggesting that either our understanding of gravity is incomplete or that unknown forces become dominant at the largest cosmic scales. But here's where the mystery becomes truly unsettling. Computer simulations of cosmic structure formation predict that superclusters should collapse unless the universe contains approximately 70% dark energy, a completely unknown form of energy that exerts negative pressure throughout space. Without dark energy, every supercluster in the observable universe should have collapsed into massive black holes billions of years ago. The fact that superclusters exist and remain stable is essentially our primary evidence that the universe is dominated by an invisible energy field that we don't understand. The implications extend far beyond just academic cosmology. The stability of superclusters directly determines the long-term habitability of the universe. If superclusters were to collapse, the resulting gravitational disruptions would eject most galaxies from their local gravitational environments, sending them into the expanding voids between superclusters where star formation would gradually cease and cosmic evolution would effectively end. Tonight, we're going to unravel this cosmic paradox by journeying from the initial formation of the first gravitational structures in the early universe, through the complex dynamics of dark matter and cosmic expansion, to the profound implications for the ultimate fate of cosmic structure formation. You'll discover why the largest structures in the universe represent the battleground between gravity and cosmic expansion, and how this battle determines whether the universe will remain architecturally rich or gradually dissolve into isolated, lonely islands of matter separated by ever-expanding voids. If you are fascinated by the hidden forces that determine cosmic architecture and the ultimate fate of structure in the universe, hit that subscribe button and give this video a thumbs up. And here is a question that will make perfect sense by the end. If you could adjust the strength of dark energy, what would happen to supercluster stability? And how would that change the long-term evolution of cosmic structure? Drop your most thoughtful predictions in the comments. I'll pin the most insightful analysis. We're about to discover that the universe operates according to a delicate balance of forces that becomes visible only at the largest observable scales. The superclusters that define cosmic architecture represent the outcome of a cosmic tug-of-war between gravity and expansion that has been playing out for nearly 14 billion years and will determine the ultimate structure of reality itself. Cosmic architecture. The magnificent architecture of the cosmic web, superclusters connected by filaments of galaxies separated by vast cosmic voids, represents the largest scale organization of matter in the observable universe, yet this architecture exists in a state of dynamic equilibrium that defies our intuition about how gravitational systems should behave over cosmic time scales. To understand why superclusters don't collapse, we first need to appreciate what superclusters actually are and how they differ from smaller gravitational systems. And like galaxy clusters, which are gravitationally bound systems where member galaxies orbit a common center of mass, superclusters represent loose associations of galaxy clusters and groups that are connected by the cosmic web but are not gravitationally bound as single unified systems. Our local supercluster, also known as the Laniakea supercluster, contains over 100,000 galaxies organized into several major galaxy clusters, including the Virgo cluster, the Hydra Centaurus region, and the Pavo Indus chain. Dr. Brent Tully's team at the University of Hawaii mapped this structure using galaxy velocity data, revealing that we live within a coherent flow pattern spanning 500 million light-years across, with all constituent galaxies moving toward a gravitational attractor called the Great Attractor. But here is where supercluster architecture becomes truly remarkable. Despite containing enough matter to gravitationally bind these structures into single, massive systems, superclusters exist in a state where their overall expansion rate exactly matches the local Hubble flow. The component galaxy clusters are moving apart from each other at the same rate that cosmic expansion drives the separation of unrelated structures throughout the universe. Recent measurements using Type-1 supernovas as standard candles have revealed that superclusters exhibit what cosmologists call linear expansion. Their internal dimensions grow proportionally to the scale factor of cosmic expansion. Dr. Adam Rees's observations show that supercluster expansion follows the same Hubble-Lemaître relationship that governs cosmic expansion generally, with velocity proportional to distance according to V equals hdd. This creates a fundamental puzzle. How can structures with such enormous gravitational mass exhibit expansion dynamics identical to regions of space with no gravitational mass at all? The gravitational binding energy of superclusters should be sufficient to decouple them from cosmic expansion, creating gravitationally bound systems that contract while the universe expands around them. To understand this paradox, we need to consider the timescales involved in gravitational collapse versus cosmic expansion. Dr. Michael Turner at the University of Chicago has calculated that a typical supercluster, if left to collapse under its own gravity without cosmic expansion, would reach maximum compression in approximately 10 to 20 billion years, comparable to the current age of the universe. However, Cosmic expansion provides a competing influence that operates on identical timescales. The expansion of space itself carries supercluster components apart at velocities that increase with distance, creating an outward force that directly opposes gravitational contraction. The question becomes whether gravitational attraction or cosmic expansion dominates the long-term evolution of these massive structures. The mathematics of this competition reveal a critical threshold that determines supercluster stability. Structures can only remain gravitationally bound if their density exceeds the critical density of the universe by a factor that depends on the cosmic expansion rate. Dr. James Peebles at Princeton University showed that this critical overdensity threshold increases over cosmic time as dark energy accelerates cosmic expansion. Current observations indicate that superclusters exist precisely at this critical threshold. They contain just enough mass to begin gravitational collapse. But cosmic expansion prevents the collapse from completing. This represents a remarkable cosmic coincidence. Superclusters are perfectly balanced between gravitational collapse and cosmic expansion, existing in a state of dynamic equilibrium that could persist for many billions of years. But the architecture of superclusters reveals even more subtle physics. The cosmic web structure filaments. Connecting massive nodes creates non-spherical mass distributions that complicate gravitational collapse dynamics. Dr. Rien van de Wegeert at the University of Groningen has shown that these elongated structures experience different gravitational forces along different axes, leading to complex collapse patterns that can be interrupted by cosmic expansion. Recent numerical simulations performed at the Max Planck Institute reveal that supercluster evolution involves a complex interplay between gravitational collapse along the shortest axis, continued expansion along the longest axis, and intermediate behavior along the middle axis. These structures don't simply expand or contract uniformly, they evolve through shape changes that reflect the competition between gravity and cosmic expansion. The observational evidence for supercluster stability comes from multiple sources. Galaxy redshift surveys like the Sloan Digital Sky Survey show that supercluster velocity patterns remain remarkably stable over the timescales that astronomical observations can probe. The internal structure of superclusters shows no evidence of the infall patterns that would characterize gravitational collapse. Dr. Carlos Franque's group at Durham University has used computer simulations to model supercluster evolution over cosmic time and found that these structures can maintain their basic architecture for periods exceeding the current age of the universe, provided that cosmic expansion continues to accelerate due to dark energy. Without dark energy acceleration, superclusters would indeed collapse within a few billion years. But perhaps the most profound aspect of supercluster architecture involves what it reveals about the transition between gravitational binding and cosmic expansion. Galaxy clusters, smaller structures typically spanning 10 to 30 million light-years, remain gravitationally bound and continue to grow through accretion of surrounding matter. Superclusters, larger structures spanning 100 to 500 million light-years, cannot achieve gravitational binding and instead follow cosmic expansion. This transition occurs at a characteristic scale called the turnaround radius, the distance from a gravitational center where cosmic expansion exactly balances gravitational attraction. Dr. Yehuda Hoffman at Hebrew University has calculated that this radius depends on both the local mass density and the cosmic expansion rate, creating a scale-dependent transition between bound and unbound structures. The existence of this transition scale reveals something fundamental about cosmic architecture. There exists a maximum size for gravitationally bound structures that is determined by the competition between local gravity and global cosmic expansion. Superclusters represent structures that approach this maximum size but cannot exceed it without losing gravitational coherence. Recent observations of supercluster dynamics using peculiar velocity measurements have confirmed that these structures exist precisely at the boundary between gravitational binding and cosmic expansion. Dr. Alun Courtois' analysis of galaxy motions within superclusters shows velocity patterns consistent with structures that are just beginning gravitational collapse but are prevented from completing the collapse by cosmic expansion. The cosmic web architecture that connects superclusters also plays a crucial role in their stability. The filamentary structure of dark matter creates anisotropic gravitational fields that channel matter flow along preferred directions, potentially stabilizing superclusters against spherical collapse while allowing continued growth. Along filamentary axes, understanding supercluster architecture also illuminates the role of dark matter in cosmic structure formation. The visible galaxies that define supercluster boundaries represent only the luminous tracers of much more massive dark matter structures. Dr. Volker Sprengel's Millennium simulation shows that dark matter halos provide the gravitational scaffolding that determines supercluster architecture, with visible galaxies forming where dark matter concentrations exceed critical density thresholds. Modern observations using gravitational lensing can directly map the dark matter distribution within superclusters, revealing that these structures contain dark matter masses exceeding their visible matter content by factors of 5 to 10. This dark matter provides the gravitational mass that should drive supercluster collapse, yet somehow fails to do so due to cosmic expansion effects. As we prepare to explore the historical formation of these massive structures, remember that supercluster architecture represents the largest scale organization of matter in the universe, where gravity and cosmic expansion exist in delicate balance. The stability of these structures depends on cosmic forces that operate far beyond the scales of direct human experience, yet determine the ultimate fate of cosmic architecture itself. The question that emerges from understanding supercluster architecture is profound. If these structures represent the maximum scale of gravitational organization, what does their stability tell us about the fundamental forces that will determine cosmic evolution over the next hundreds of billions of years? Formation history. The formation of superclusters represents one of the most remarkable transformations in cosmic history, a gradual process spanning billions of years, during which tiny quantum fluctuations in the early universe grew through gravitational amplification to become the largest coherent structures in the observable cosmos. Yet this formation process contains within it the very mechanism that prevents their ultimate gravitational collapse. To understand how superclusters form without collapsing, we need to journey back to the cosmic dark ages, approximately 380,000 years after the Big Bang, when the universe first became transparent to light and gravity began its slow work of amplifying the minute density fluctuations that quantum mechanics had imprinted during cosmic inflation. At this epoch, the universe was remarkably smooth. Density variations amounted to only about 1 part in 100,000. Dr. George Smoot's analysis of cosmic microwave background data from the COBE satellite first revealed these primordial fluctuations, showing a universe filled with density variations so small that they would seem completely insignificant by any reasonable measure. Yet these tiny variations contain the seeds of all future cosmic structure. The early formation process operated through what cosmologists call hierarchical structure formation. Small density fluctuations collapsed first, forming the first generation of dark matter halos, which then merged to form progressively larger structures over cosmic time. Dr. Simon White at the Max Planck Institute demonstrated that this bottom-up formation process naturally produces the cosmic web architecture we observe today. But here's where the formation history becomes crucial for understanding supercluster stability. The hierarchical formation process operates under continuous competition between gravitational collapse and cosmic expansion. Structures that begin collapsing early in cosmic history, when the universe was denser and expansion was slower, can achieve gravitational binding and decouple from cosmic expansion. Structures that begin forming later face increasingly difficult conditions as cosmic expansion accelerates. Recent analysis of galaxy formation epochs using deep field observations from the James Webb Space Telescope reveals that the first galaxies formed when the universe was only a few 100 million years old. Dr. Garth Illingworth's observations show that these early galaxies formed within dark matter halos that could achieve gravitational binding because cosmic expansion was still dominated by matter rather than dark energy. Galaxy clusters, the dense cores of what would eventually become superclusters, formed through the merger of these early galaxy groups during the first few billion years of cosmic history. Dr. Bradford Holden's studies of high-redshift galaxy clusters show that these structures achieved gravitational binding when cosmic expansion was slower. allowing them to decouple from the Hubble flow and continue growing through accretion. However, the larger-scale supercluster structures began forming later in cosmic history, when dark energy was becoming an increasingly important component of cosmic expansion. Dr. Sean Cole at Durham University has used large-scale structure simulations to show that supercluster formation occurred primarily during the last 8 to 10 billion years. Precisely the epoch when dark energy began dominating cosmic expansion dynamics. This timing explains the paradox of supercluster formation without collapse. These structures began forming during an epoch when cosmic expansion was transitioning from deceleration to acceleration. Due to dark energy, the gravitational collapse that initiated supercluster formation could proceed initially, but as cosmic expansion accelerated, the collapse process was gradually overwhelmed by expansion forces. The mathematical description of this process involves the competition between two characteristic timescales. The gravitational collapse timescale T_grav approximately equals 1 square root g, where g is the gravitational constant and ρ is the local density. And the cosmic expansion timescale T_exp approximately equals 1 hg, where hc is the Hubble parameter at redshift z. Structures can achieve gravitational binding only if T_grav T_exp. Dr. Volker Springel's Millennium simulation demonstrates that this competition creates a characteristic transition epoch around redshift z approximately equals 1. Approximately 6 billion years ago, when cosmic expansion began winning the competition against gravitational collapse for the largest scale structures, galaxy clusters that formed before this epoch could achieve binding, while larger supercluster structures that formed afterward could not. But the formation history reveals even more subtle effects. The cosmic web structure that characterizes superclusters formed through gravitational instability operating on nonlinear density perturbations. Dr. Yanni Nasto's analysis shows that these nonlinear effects create anisotropic collapse patterns where gravitational forces operate differently along different spatial axes. Recent computer simulations by Dr. Anatoly Klipin at New Mexico State University reveal that supercluster formation involves a complex sequence of events: initial gravitational amplification of density fluctuations, nonlinear collapse along the shortest axis to form cosmic web filaments, continued expansion along the longest axis due to cosmic expansion, and intermediate behavior that creates the flattened, elongated structures we observe as supercluster architecture. The observational evidence for this formation history comes from studies of galaxy formation rates as functions of cosmic time. Dr. Mauro Javalisco's analysis of deep field observations shows that galaxy formation rates peaked approximately 10 billion years ago, corresponding precisely to the epoch when supercluster formation was most active. Cosmic expansion was beginning its transition to dark energy dominance. This formation epoch also explains why different components of superclusters exhibit different dynamical states. Galaxy clusters, which formed early and achieved gravitational binding, continue to grow through accretion and show clear signs of ongoing gravitational collapse. The larger-scale supercluster structures, which formed later, show velocity patterns consistent with structures that began collapsing but were prevented from completing the collapse process. Dr. Martha Haynes' analysis of galaxy redshift data from the Arecibo Legacy Fast Alpha survey reveals that supercluster velocity patterns preserve signatures of their formation history. Galaxies in the densest regions show evidence of gravitational inflow that began billions of years ago but has been gradually slowing due to cosmic expansion acceleration. The role of dark matter in supercluster formation history is particularly crucial. Dark matter provides the gravitational scaffolding that determines where and when supercluster formation begins. But dark matter dynamics are also strongly affected by cosmic expansion. Dr. Carlos Frank's analysis shows that dark matter halos that exceed certain mass thresholds can achieve gravitational binding, while larger structures remain coupled to cosmic expansion. Recent observations using weak gravitational lensing can directly probe the dark matter distribution in forming superclusters, revealing how dark matter dynamics evolved during supercluster formation. Dr. Catherine Heyman's analysis of cosmic shear data shows that supercluster dark matter structures exhibit signatures of interrupted gravitational collapse density profiles that began steepening due to gravitational contraction but were frozen in place by cosmic expansion acceleration. But perhaps the most profound aspect of supercluster formation history involves what it reveals about cosmic timing. The universe underwent a fundamental transition approximately 6 billion years ago when dark energy began dominating cosmic dynamics. Superclusters represent the last generation of large-scale structures that could begin forming before this transition. And their current stability reflects the cosmic pause in structure formation that occurred as dark energy took over. Understanding this formation history also illuminates why superclusters will never collapse in the future. The cosmic expansion rate continues to accelerate due to dark energy, meaning that the competition between gravitational collapse and cosmic expansion will continue shifting in favor of expansion. Structures that couldn't achieve gravitational binding during the epoch of maximum structure formation will certainly never achieve binding as cosmic expansion accelerates further. The formation history also reveals connections between supercluster stability and the fundamental properties of dark energy. If dark energy properties were significantly different, if the dark energy equation of state differed from W approximately equals -1, then supercluster formation history would have proceeded differently, potentially allowing these structures to achieve gravitational binding or preventing their formation entirely. Modern surveys like the Dark Energy Survey are using observations of supercluster formation history to constrain the properties of dark energy and test theories of cosmic acceleration. Dr. Josh Freeman's analysis shows that supercluster formation rates and collapse dynamics provide sensitive probes of dark energy physics that complement other cosmological tests. As we prepare to explore the gravitational dynamics that govern supercluster evolution, remember that the formation history we've examined reveals superclusters as products of a specific epoch in cosmic evolution, structures that began forming when gravity was still competitive with cosmic expansion but completed their formation after cosmic expansion gained the upper hand. The question that emerges from understanding supercluster formation history is profound. If these structures represent the last generation of large-scale cosmic architecture, what will happen to cosmic structure formation as dark energy continues to dominate cosmic expansion over the next hundreds of billions of years? Gravitational dynamics. The gravitational dynamics governing supercluster evolution reveal one of the most subtle and complex force balances in the universe. A three-way competition between gravitational attraction, cosmic expansion, and dark energy acceleration that determines whether the largest structures in the cosmos will contract, remain stable, or gradually dissolve over cosmic time scales. To understand these dynamics, we need to appreciate that superclusters exist in a gravitational regime unlike any other cosmic structure. And like galaxy clusters, where gravitational forces clearly dominate and produce bound systems with well-defined centers of mass, superclusters operate in a regime where gravitational forces are comparable to, but slightly weaker than, the forces driving cosmic expansion. Dr. James Peebles at Princeton University developed the fundamental equations describing this regime through his analysis of cosmic structure formation. In the linear perturbation theory that describes early structure growth, density perturbations grow as delta T varies as a T in a matter-dominated universe, where a T is the scale factor. However, once dark energy begins dominating cosmic expansion, perturbation growth essentially stops, freezing structure formation at the scale that corresponds to modern superclusters. The mathematical framework reveals why superclusters represent a special case in gravitational dynamics. Recent numerical simulations by Dr. Anatoly Klipin have revealed that supercluster gravitational dynamics exhibit what physicists call quasi-static evolution. The structures evolve slowly compared to gravitational dynamical timescales because the competing forces nearly cancel each other. This creates a regime where small changes in cosmic parameters can dramatically affect long-term evolution. But the gravitational dynamics become even more complex when we consider that superclusters are not spherical mass distributions. The cosmic web structure creates highly anisotropic gravitational fields where gravitational forces operate differently along different spatial directions. Dr. Reen van de Wekert's analysis shows that these anisotropic forces can stabilize structures against collapse along some axes while allowing continued expansion along others. The observational evidence for these complex gravitational dynamics comes from peculiar velocity measurements observations of galaxy motions relative to the cosmic expansion flow. Dr. Alan Dressler's analysis of galaxy velocities within superclusters reveals motion patterns consistent with gravitational fields that are strong enough to perturb galaxy motions, but not strong enough to create bound orbital systems. Recent measurements using improved distance indicators like surface brightness fluctuations have enabled more precise mapping of supercluster gravitational fields. Dr. John Tonry's observations show that galaxies within superclusters exhibit systematic velocity deviations from pure Hubble flow that reflect ongoing gravitational interactions. But these interactions are not strong enough to prevent overall expansion. The role of dark matter in supercluster gravitational dynamics is particularly important because dark matter provides approximately 85% of the gravitational mass. Dr. Volker-Springville's Millennium simulation reveals that dark matter halo dynamics within superclusters follow complex patterns where individual halos can maintain their integrity while the overall supercluster structure expands. Computer simulations show that dark matter dynamics in superclusters exhibit what cosmologists call violent relaxation, a process where gravitational interactions between dark matter particles lead to equilibrium configurations that can persist for billions of years. Dr. Jeremiah Oestreicher's analysis demonstrates that this relaxation process can create gravitationally stable configurations even in expanding systems. But perhaps the most remarkable aspect of supercluster gravitational dynamics involves the presence of turnaround surfaces, spherical boundaries around massive structures where gravitational attraction exactly balances cosmic expansion. Dr. Romain Tessier's simulations show that these surfaces represent the maximum extent to which gravitational structures can grow in an expanding universe. The mathematics of turnaround dynamics reveal that the turnaround radius r_τ for a spherical mass distribution follows the relationship r_t varies as gm per h squared 1/3, where m is the enclosed mass and h is the Hubble parameter for typical supercluster masses. This radius corresponds to dimensions of 100 to 200 million light-years, precisely the observed scale of supercluster structures. Recent observations of galaxy infall patterns around massive galaxy clusters have enabled direct detection of turnaround surfaces in real cosmic structures. Dr. Yehuda Hoffman's analysis of galaxy velocities around the Virgo cluster shows clear evidence of a turnaround surface at approximately 10 million light-years from the cluster center. Where galaxy infall velocities transition to Hubble expansion, the existence of turnaround surfaces explains why superclusters can maintain coherent structure without collapsing. These structures represent gravitational systems that have expanded to their turnaround radii and now exist in dynamic equilibrium between gravitational attraction and cosmic expansion. The gravitational forces are strong enough to halt expansion, but not strong enough to drive contraction. But the gravitational dynamics also reveal the crucial role of cosmic acceleration in preventing supercluster collapse. As dark energy continues to accelerate cosmic expansion, the Hubble parameter h increases over time, which increases the turnaround radius and allows gravitationally marginal structures to expand rather than contract. Dr. Michael Turner's calculations show that without dark energy acceleration, superclusters would indeed collapse under their own gravity. The observational signatures of these complex gravitational dynamics appear in multiple astronomical phenomena. Gravitational lensing observations can directly map the gravitational fields of superclusters, revealing mass distributions that create the gravitational forces we calculate theoretically. Dr. Jean-Paul Niebes' analysis of strong lensing in galaxy clusters shows gravitational fields consistent with structures approaching but not exceeding gravitational binding thresholds. Recent advances in weak gravitational lensing surveys have enabled statistical studies of supercluster gravitational dynamics across large cosmological volumes. Dr. Catherine Hayman's analysis of cosmic shear data from the kilodegree survey reveals that supercluster mass distributions exhibit signatures of gravitational dynamics that are consistent with structures in quasi-static equilibrium. The three-body and n-body dynamics within superclusters also contribute to their stability against collapse. Dr. Scott Tremaine's analysis shows that gravitational interactions between galaxy clusters within superclusters can transfer energy and angular momentum in ways that stabilize the overall system against collapse, similar to how planetary dynamics can stabilize solar systems against gravitational instabilities. Modern computational cosmology has enabled detailed studies of supercluster gravitational dynamics using simulations with billions of dark matter particles. Dr. Carlos Frank-Siegel's simulations reveal that supercluster gravitational evolution involves complex feedback processes between dark matter dynamics, galaxy formation, and cosmic expansion that maintain quasi-static equilibrium over cosmic time scales. But perhaps the most profound aspect of supercluster gravitational dynamics involves what they reveal about the fundamental nature of gravity itself. These structures operate in a regime where gravitational forces are weak enough that relativistic effects and quantum corrections could potentially become important. Some theories of modified gravity predict different behavior for supercluster dynamics compared to Einstein's general relativity. Dr. Bhuvnesh analysis of supercluster dynamics provides tests of alternative theories of gravity that predict deviations from general relativity on cosmic scales. Observations of supercluster stability and evolution can potentially distinguish between different theories of gravity and dark energy, making these structures natural laboratories for fundamental physics. The role of cosmic voids in supercluster gravitational dynamics also contributes to their stability. The large empty regions between superclusters create gravitational environments where expansion forces are enhanced relative to gravitational attraction. Dr. Enzo Brancini's analysis shows that void expansion can help stabilize neighboring supercluster structures by reducing external gravitational perturbations. Understanding supercluster gravitational dynamics also illuminates the connection between local physics and global cosmic evolution. The gravitational fields that determine supercluster stability depend sensitively on the cosmic expansion rate, dark energy properties, and the overall matter density of the universe. Changes in any of these global properties would dramatically affect supercluster evolution. As we prepare to explore how cosmic expansion specifically affects supercluster dynamics, remember that the gravitational dynamics we've examined reveal these structures as existing at a unique balance point in cosmic physics massive enough to generate significant gravitational fields, but existing in a cosmic epoch where expansion forces prevent gravitational collapse. The question that emerges from understanding supercluster gravitational dynamics is profound. If these structures represent the maximum scale, where gravitational forces can compete with cosmic expansion, what does this tell us about the ultimate limits of structure formation in an accelerating universe? Expansion effects. The effects of cosmic expansion on supercluster dynamics reveal one of the most fundamental aspects of modern cosmology. Space itself is expanding at a rate that increases with distance, creating an ever-strengthening outward force that operates on all scales but becomes dominant precisely at the supercluster scale, where it overwhelms gravitational collapse and determines the ultimate fate of cosmic structure. To understand how cosmic expansion prevents supercluster collapse, we need to appreciate that expansion doesn't simply carry objects apart through space. It represents the continuous creation of new space between all objects, generating what physicists call cosmological acceleration that acts like an anti-gravitational force with strength proportional to distance. The Hubble-Lemaître law, V equals hDD, describes this expansion with elegant simplicity. Recession velocity increases linearly with distance, where h approximately equals 70 km per second. MPC represents the current expansion rate. Dr. Adam Rees's precise measurements using Typeus supernovae show that this relationship holds with remarkable accuracy across cosmic distances, revealing expansion as a fundamental property of spacetime itself rather than motion through space. But the expansion effects on superclusters involve more than just the Hubble flow. Dr. Saul Perlmutter's analysis of distant supernovae first revealed this cosmic acceleration in 1998, showing that the universe's expansion rate was slower in the past and has been increasing for approximately the last 6 billion years. This discovery fundamentally changed our understanding of supercluster dynamics by revealing that expansion forces are becoming stronger over time. The mathematical description of expansion effects on gravitating systems involves the concept of peculiar acceleration, the deviation from pure Hubble flow caused by gravitational forces. For a test mass at distance r from a central mass m, the peculiar acceleration is _pec equals a gm, or squared plus her plus dh dtr, where the first term represents gravitational attraction. The second represents steady expansion, and the third represents acceleration due to dark energy. Recent numerical simulations by Dr. Anatoly Klipin demonstrate that expansion effects create a characteristic scale where gravitational attraction exactly balances expansion forces. Below this scale, gravity dominates and structures can collapse. Above this scale, expansion dominates and structures cannot achieve gravitational binding. Superclusters exist precisely at this critical scale. The observational evidence for expansion effects in superclusters comes from measurements of galaxy recession velocities as functions of position within these structures. Dr. Martha Haynes' analysis of 21 cm hydrogen observations shows that galaxies throughout superclusters follow modified Hubble flows that reflect the competition between local gravitational forces and cosmic expansion. But expansion effects on superclusters reveal a more subtle phenomenon. The expansion of space can actually stretch gravitationally bound systems if the expansion rate changes over time. Dr. Michael Turner's calculations show that accelerating expansion creates tidal forces that can disrupt marginally bound systems by stretching them faster than gravitational forces can respond. The role of dark energy in expansion effects is particularly crucial for supercluster dynamics. Dark energy acts like a cosmic fluid with negative pressure that creates repulsive gravitational effects. Dr. Sean Carroll's analysis demonstrates that dark energy acceleration produces outward forces that increase quadratically with distance, making these forces particularly important for large-scale structures. Recent observations from the Dark Energy Survey have enabled precise measurements of expansion effects on cosmic structure formation. Dr. Josh Freeman's analysis reveals that the growth rate of cosmic structures has been slowing dramatically over the past several billion years as dark energy acceleration overwhelmed gravitational amplification of density perturbations. The expansion effects also create what cosmologists call cosmic flow patterns, large-scale velocity fields that reflect the gravitational influence of massive structures. Combined with cosmic expansion, Dr. Haroon Courtois' analysis of peculiar velocity data reveals that superclusters exist within flow patterns that show clear signatures of expansion overwhelming local gravitational attraction. Computer simulations of cosmic structure formation show that expansion effects create a horizon for gravitational influence. Distant objects cannot affect local dynamics, because expansion carries them away faster than gravitational signals can propagate. Dr. Carlos France's Millennium simulation demonstrates that this horizon limits the maximum size of gravitational structures to scales comparable to observed superclusters. But perhaps the most remarkable aspect of expansion effects involves their time dependence. The transition from matter-dominated to dark energy-dominated expansion occurred when the universe was approximately half its current age. Structures that formed before this transition could achieve gravitational binding, while structures forming afterward could not overcome expansion forces. Dr. Volker Sprengel's analysis of cosmic structure formation shows that this transition created a characteristic fossil signature in cosmic structure. Galaxy clusters formed before the transition and remain gravitationally bound. Superclusters formed during the transition and exist in quasi-static equilibrium. Larger structures attempted to form after the transition, but were disrupted by acceleration. The mathematical modeling of expansion effects requires sophisticated treatments of general relativity in cosmological contexts. The Friedmann equations that describe cosmic expansion must be coupled with the Poisson equation that describes gravitational fields to properly account for the competition between expansion and gravitational collapse in realistic cosmic structures. Recent advances in observational cosmology have enabled direct detection of expansion effects on cosmic structure formation. The Planck satellite measurements of cosmic microwave background anisotropies reveal how expansion effects have modified the growth of cosmic structure over the past 13.8 billion years, showing clear signatures of the transition to dark energy dominance. But expansion effects also reveal fundamental connections between local physics and global cosmology. The expansion rate that determines supercluster dynamics depends on the global matter and energy content of the entire observable universe. Local structure formation is thus intimately connected to cosmic scale physics through expansion effects. Dr. Wayne Hu's analysis of cosmic structure formation demonstrates that expansion effects create acoustic oscillations in the matter distribution, periodic variations in density that reflect sound waves in the early universe that were frozen in place when expansion effects began dominating gravitational dynamics. These oscillations are visible in modern large-scale structure surveys. The expansion effects also create observational challenges for studying supercluster dynamics. Because expansion carries distant objects away from us, observations of distant superclusters show us these structures as they existed billions of years ago, when expansion effects were weaker. Understanding modern supercluster dynamics requires careful modeling of expansion history. Recent observations using gravitational lensing can directly probe expansion effects by measuring how cosmic structure has evolved over cosmic time. Dr. Catherine Hayman's weak lensing analysis shows that the amplitude of cosmic structure has been essentially frozen for the past several billion years due to expansion effects overwhelming gravitational amplification. The role of cosmic acceleration in expansion effects creates fundamental limits on future structure formation. As dark energy continues to accelerate expansion, the forces opposing gravitational collapse will continue strengthening. Dr. Robert Caldwell's analysis shows that current superclusters represent the largest structures that will ever form in cosmic history. But expansion effects also reveal the remarkable fine-tuning of cosmic parameters that enables complex structure formation. If expansion had been slightly faster, no large-scale structures could have formed. If expansion had been slightly slower, all matter would have collapsed into black holes. The observed expansion rate enables the rich cosmic architecture we observe. Understanding expansion effects on superclusters also provides insights into alternative theories of cosmic acceleration. Some models propose that apparent acceleration results from modifications to gravity rather than dark energy. Dr. Bhuvanesh-Jain's analysis shows that supercluster dynamics can distinguish between different theories of cosmic acceleration. As we prepare to explore the crucial role of dark energy in preventing supercluster collapse, remember that expansion effects represent the cosmic scale physics that determines whether the universe will remain architecturally rich or gradually dissolve into isolated islands of matter separated by ever-expanding voids. The question that emerges from understanding expansion effects is profound. If cosmic acceleration continues indefinitely, how will this affect the long-term evolution of superclusters and the ultimate fate of large-scale structure in the universe? Dark energy represents the most mysterious and dominant component of cosmic reality, an invisible energy field that comprises approximately 70% of the universe and exerts negative pressure throughout space, creating the accelerating expansion that prevents supercluster gravitational collapse and ultimately determines whether cosmic architecture will persist or gradually dissolve over cosmic time scales. The discovery of dark energy emerged from observations that seemed to violate fundamental expectations about cosmic evolution. When Drive.Sol Perlmutter and Dr. Adam Rees independently studied distant Typeus supernovae in the late 1990s, they expected to measure how cosmic expansion was slowing down due to gravitational attraction between cosmic structures. Instead, they discovered that expansion has been accelerating for the past 6 billion years. This acceleration requires an energy component with negative pressure, something that creates repulsive rather than attractive gravitational effects. Einstein's field equations show that the gravitational effect of any energy component depends on its energy density plus 3 times its pressure. For normal matter and radiation, this sum is positive, creating attractive gravity. Dark energy has pressure P equals rho c squared, making the sum negative and creating repulsive gravity. Dr. Michael Turner coined the term dark energy to describe this mysterious component, emphasizing that it represents a completely new form of energy unlike anything in the standard model of particle phase. ICS. The simplest model assumes dark energy behaves like Einstein's cosmological constant lambda, representing vacuum energy with constant density and negative pressure throughout space and time. Recent observations from the Planck satellite have precisely measured dark energy's contribution to cosmic dynamics. The universe contains approximately 68.3% dark energy, 26.8% dark matter, and only 4.9% ordinary matter. This means that the repulsive gravitational effects of dark energy overwhelm the attractive gravitational effects of all matter combined, explaining why cosmic expansion accelerates rather than decelerates. Dark energy but dark energies' role in supercluster dynamics goes beyond just accelerating cosmic expansion. Dr. Sean Carroll's analysis at Caltech demonstrates that this distance proportional repulsion becomes dominant at scales exceeding approximately 100 million light-years, precisely the scale that Sharat arises superclusters. Below this scale, gravitational attraction from local matter density can overcome dark energy repulsion. Above this scale, dark energy repulsion overwhelms gravitational attraction and prevents structure formation. The mathematical description of dark energy effects on gravitating systems involves modifying the Poisson equation that describes gravitational fields as squared phi equals for g rho underscore matter to rho underscore dark underscore energy, where phi represents the gravitational potential. The negative contribution from dark energy creates effective anti-gravity that opposes matter's gravitational attraction. Recent computer simulations by Dr. Volker Springel have modeled cosmic structure formation including dark energy effects and confirmed that dark energy prevents supercluster gravitational collapse. Without dark energy, these simulations show that superclusters would collapse into massive black holes within a few billion years. Dark energy maintains quasi-static equilibrium by providing precisely the right amount of repulsive acceleration. But dark energy also reveals fundamental questions about the nature of vacuum energy and quantum field theory. Quantum mechanics predicts that empty space contains zero-point energy from quantum vacuum fluctuations. However, naive calculations suggest this vacuum energy should be 120 orders of magnitude larger than observed dark energy density, the worst prediction in the history of physics. Dr. Steven Weinberg's analysis of this cosmological constant problem suggests that dark energy might not represent vacuum energy but rather a new type of energy field, with properties specifically tuned to enable structure formation. The observed dark energy density is remarkably close to the critical value that allows complex structures like galaxies and stars to form while preventing universal gravitational collapse. The observational evidence for dark energy comes from multiple independent sources. Type Ia supernova observations show cosmic acceleration. Cosmic microwave background measurements reveal the universe's geometry and energy content. Baryon acoustic oscillations provide standard rulers that trace expansion history. Large-scale structure surveys map how cosmic structure formation has slowed due to dark energy. Recent advances in observational cosmology have enabled increasingly precise measurements of dark energy properties. The Dark Energy Survey has mapped hundreds of millions of galaxies to measure how cosmic structure growth has evolved over cosmic time. Dr. Josh Freeman's analysis shows that structure growth essentially stopped approximately 6 billion years ago when dark energy began dominating cosmic dynamics. But perhaps the most profound mystery involves dark energy's apparent fine-tuning for structure formation. If dark energy density were much larger, cosmic acceleration would prevent all structure formation. If dark energy density were much smaller, the universe would collapse gravitationally before complex structures could form. The observed value enables the rich cosmic architecture we inhabit. Dr. Max Tegmark's analysis of cosmic fine-tuning suggests that dark energy density must lie within a narrow range, approximately 1 part in 10,120, to enable structure formation without preventing cosmic evolution. This extraordinary fine-tuning raises profound questions about whether our universe represents one realization among countless others with different dark energy properties. The theoretical possibilities for dark energy extend beyond simple cosmological constant models. Quintessence theories propose that dark energy represents a dynamical scalar field that can evolve over cosmic time. Phantom dark energy models suggest acceleration that increases over time, potentially leading to big rip scenarios where expansion eventually tears apart all matter structures. Recent observations using gravitational wave detectors provide new probes of dark energy through their effects on cosmic expansion history. The LIGO-Virgo collaboration's measurements of neutron star mergers enable independent determination of the Hubble constant, helping to constrain dark energy properties through precision cosmology. But dark energy also connects to fundamental questions about the nature of spacetime itself. Some theories propose that apparent dark energy results from modifications to general relativity on cosmic scales rather than representing a new energy component. Dr. Bhuvnesh Jain's analysis shows that supercluster dynamics can potentially distinguish between dark energy and modified gravity explanations. The role of dark energy in cosmic evolution extends far beyond preventing supercluster collapse. Dark energy acceleration will eventually overcome gravitational binding at progressively smaller scales, potentially disrupting galaxy clusters, galaxies, and ultimately all gravitationally bound structures in a process cosmologists call cosmic doomsday or the Big Rip. Dr. Robert Caldwell's analysis of extreme dark energy models shows that if dark energy density increases over time, phantom dark energy, cosmic acceleration will eventually overcome all fundamental forces, tearing apart atoms themselves in a finite time. Even for constant dark energy density, acceleration will gradually isolate all cosmic structures as expansion carries them beyond each other's gravitational influence. Recent observations of cosmic microwave background polarization provide additional constraints on dark energy through its effects on cosmic reionization and structure formation. The Planck satellite data reveals how dark energy influenced the formation of the first stars and galaxies by determining when gravitational collapse could overcome expansion forces. The connection between dark energy and quantum field theory suggests that understanding dark energy might require new physics beyond the standard model. String theory, loop quantum gravity, and other approaches to quantum gravity all make different predictions about vacuum energy and cosmic acceleration that could potentially be tested through precision and measurements of dark energy properties. Modern dark energy research focuses on measuring the equation of state parameter W equals Pc, which equals -1 for cosmological constant dark energy but could differ for more exotic models. Dr. Drogan Huter's analysis shows that current observations are consistent with W equals -1 but cannot rule out small deviations that might reveal the true nature of dark energy. But perhaps the most profound implication involves what dark energy reveals about cosmic destiny. The accelerating expansion driven by dark energy suggests that our current epoch, when complex structures like superclusters exist in quasi-static equilibrium, represents a temporary phase in cosmic evolution. Future cosmic evolution will be dominated by dark energy acceleration that gradually destroys all structure. Understanding dark energy also illuminates the remarkable cosmic coincidence that we exist during the epoch when dark energy and matter densities are comparable. In the past, matter dominated and structure could form. In the future, dark energy will dominate and structure formation will cease. We inhabit the brief cosmic moment when these energies balance. As we prepare to explore how dark matter provides the gravitational scaffolding for supercluster formation, remember that dark energy represents the cosmic force that ultimately determines the fate of large-scale structure. The mysterious energy field that prevents supercluster collapse also sets the ultimate limits on cosmic architecture and complexity. The question that emerges from understanding dark energy is profound. If this mysterious component dominates cosmic evolution and will eventually overcome all gravitational structures, what does this reveal about the fundamental nature of reality and the ultimate fate of complexity in the universe? Dark matter represents an invisible gravitational scaffolding that enables supercluster formation while simultaneously demonstrating why these massive structures cannot achieve the gravitational densities required for collapse. A cosmic substance that comprises 85% of all matter yet interacts only through gravity, creating the cosmic web architecture that defines large-scale structure while remaining perpetually unable to concentrate sufficiently to overcome cosmic expansion. The discovery that cosmic structure formation requires dark matter emerged from observations that visible matter alone cannot account for the gravitational effects observed in galaxies and galaxy clusters. Dr. Vera Rubin's pioneering measurements of galaxy rotation curves in the 1970s revealed that galaxies contain approximately 5 times more mass than can be accounted for by visible stars and gas, requiring an invisible matter component to explain observed gravitational dynamics. But the role of dark matter in supercluster dynamics involves far more than just providing additional gravitational mass. Computer simulations of cosmic structure formation show that dark matter particles interact only through gravity, allowing them to form the cosmic web structure of filaments and nodes that channels ordinary matter into the galaxy clusters and superclusters we observe today. Dr. Carlos Franque's analysis using the Millennium simulation demonstrates that dark matter halos provide the gravitational potential wells where ordinary matter accumulates to form galaxies. The hierarchical formation of dark matter structure, small halos merging to form progressively larger structures, determines the timing and location of galaxy formation throughout cosmic history. Recent observations using gravitational lensing have enabled direct detection of dark matter structure in superclusters. Dr. Richard Nassius' analysis of cosmic shear data reveals dark matter filaments connecting galaxy clusters across tens of millions of light-years, confirming theoretical predictions about cosmic web architecture and showing that superclusters trace the underlying dark matter distribution. Dark matter. The mathematics of dark matter dynamics in superclusters involves n-body gravitational calculations with millions or billions of particles. Dr. Volker Sprengel's cosmological simulations show that dark matter evolves according to collisionless dynamics, where individual particles follow geodesics in the evolving gravitational field created by all other particles combined. But dark matter's role in preventing supercluster collapse emerges from its inability to dissipate energy through electromagnetic interactions. Unlike ordinary matter, which can cool through radiation and collapse to high densities, dark matter remains collisionless and cannot concentrate beyond limits imposed by gravitational dynamics and cosmic expansion. Dr. Jeremiah Ostraker's analysis of dark matter halo formation shows that collisionless gravitational systems naturally develop density profiles that follow universal relationships. Recent high-resolution simulations by Dr. Julio Navarro reveal that dark matter halos exhibit complex substructure with numerous smaller halos embedded within larger structures. This hierarchical substructure reflects the bottom-up formation process and creates gravitational environments where smaller structures can remain stable even within larger gravitational systems. The observational evidence for dark matter in superclusters comes from multiple sources. Galaxy velocity measurements reveal gravitational fields that require dark matter to explain observed dynamics. X-ray observations of hot gas in galaxy clusters show temperature and density profiles consistent with dark matter gravitational potentials. Gravitational lensing directly maps dark matter distribution through its effects on background galaxies. But perhaps the most remarkable aspect of dark matter involves its apparent fine-tuning for structure formation. If dark matter interacted more strongly with itself or with ordinary matter, it would cool and concentrate, potentially forming structures too dense for galaxy formation. If dark matter interacted more weakly, it couldn't form the gravitational scaffolding required for cosmic structure formation. Dr. Sean Carroll's analysis suggests that dark matter properties must lie within narrow ranges to enable the cosmic architecture we observe. The dark matter particle mass, interaction cross-section, and abundance all appear to be precisely tuned to create cosmic web structure while preventing excessive concentration that would lead to premature gravitational collapse. The role of dark matter in cosmic structure formation also reveals fundamental connections between particle physics and cosmology. Leading candidates for dark matter include weakly interacting massive particles WIMPs predicted by supersymmetric extensions to the Standard Model, axions from string theory, and sterile neutrinos from extended particle theories, recent direct detection experiments. Searching for dark matter particles have constrained the interaction strength between dark matter and ordinary matter to extraordinarily small values. But dark matter's role in supercluster dynamics also reveals why these structures cannot collapse gravitationally. Dark matter halos reach equilibrium configurations through a process called violent relaxation, where gravitational interactions lead to stable density distributions that resist further collapse. Dr. Lyndon Bell's analysis shows that this process creates quasi-steady configurations that can persist for billions of years. Computer simulations of dark matter halo mergers show that when two large dark matter halos collide, they don't simply combine into a more compact structure. Instead, gravitational interactions redistribute energy and angular momentum in ways that typically create larger, less concentrated configurations. This process prevents the progressive concentration that would be required for supercluster gravitational collapse. The observational consequences of dark matter dynamics appear in cosmic structure formation patterns. Dr. Riza Wexler's analysis of galaxy formation simulations shows that the observed properties of galaxy clusters and superclusters, their sizes, masses, and internal structure can be explained quantitatively by dark matter models that include cosmic expansion effects. Recent measurements of cosmic structure on the largest scales provide direct tests of dark matter physics. The Sloan Digital Sky Survey measurements of boron acoustic oscillations reveal how dark matter and ordinary matter evolved differently during cosmic structure formation, with dark matter beginning collapse earlier while ordinary matter remained coupled to radiation. But dark matter also reveals fundamental limits on cosmic structure formation. The finite velocity dispersion of dark matter particles creates a minimum scale below which structure cannot form the free streaming scale that depends on dark matter particle properties. For typical WIMP dark matter, this scale corresponds to structures smaller than Earth, allowing all observed cosmic structures to form. The distribution of dark matter within superclusters shows signatures of the ongoing competition between gravitational collapse and cosmic expansion. Dr. Ben Morris' analysis of dark matter substructure shows that smaller dark matter halos within superclusters maintain their integrity despite tidal forces from larger structures, demonstrating the stability of dark matter configurations against external perturbations. Recent advances in computational cosmology have enabled simulations of cosmic structure formation with unprecedented resolution and dynamic range. The illustrating simulations include both dark matter and ordinary matter physics, revealing how these components interact during supercluster formation and evolution. But perhaps the most profound aspect of dark matter involves what it reveals about cosmic composition. The fact that the vast majority of cosmic matter consists of particles that interact only gravitationally suggests that the electromagnetic processes that dominate human experience represent only a tiny fraction of cosmic physics. Dr. Catherine Freese's analysis of dark matter cosmology shows that the universe we can directly observe, stars, planets, galaxies, represents less than 5% of cosmic reality. The remaining 95% consists of dark matter and dark energy that interact through gravitational forces we can observe but don't fundamentally understand. Understanding dark matter dynamics also illuminates why superclusters represent the maximum scale of cosmic structure. Dark matter halos can grow through accretion and mergers until cosmic expansion becomes strong enough to prevent further growth. Superclusters represent dark matter structures that achieved maximum size just as cosmic expansion began overwhelming gravitational collapse. The role of dark matter in cosmic evolution extends far beyond structure formation. Dark matter annihilation might produce observable signatures through gamma rays, positrons, or neutrinos that could reveal dark matter particle properties. Dr. Dan Hooper's analysis of potential dark matter signals shows that supercluster-scale dark matter distributions might produce detectable astrophysical signals. Modern surveys are mapping dark matter distribution throughout cosmic superclusters using weak gravitational lensing techniques. Dr. Catherine Heymans's analysis of the kilodegree survey reveals how dark matter structure evolved over cosmic time, showing how the transition to dark energy domination affected dark matter halo growth rates. As we prepare to explore the cosmic web architecture that connects superclusters, remember that dark matter provides the invisible foundation for all large-scale cosmic structure while simultaneously demonstrating why gravitational collapse cannot proceed indefinitely in an expanding universe dominated by dark energy. The question that emerges from understanding dark matter dynamics is profound. If the vast majority of cosmic matter consists of particles we cannot directly detect, what does this reveal about the hidden complexity of cosmic reality and our limited perspective on the true nature of the universe? Cosmic web. The cosmic web represents the largest scale architecture in the universe, a vast network of dark matter filaments connecting massive nodes where superclusters form separated by enormous voids that contain almost no matter, creating a structure that determines why superclusters can form along filamentary connections but cannot collapse into single massive objects due to the geometry and dynamics of web-like gravitational architecture. To understand how the cosmic web prevents supercluster collapse, we need to appreciate that this structure represents the three-dimensional manifestation of gravitational instability operating on primordial density fluctuations that were nearly uniform, but contain tiny variations imprinted by quantum fluctuations during cosmic inflation 13.8 billion years ago. Dr. Zeldovich's pioneering analysis in the 1970s predicted that gravitational collapse of initially small density perturbations would create pancake-like structures that intersect to form filaments, which in turn intersect to form dense nodes. This Zeldovich approximation successfully predicted the cosmic web architecture decades before observations confirmed its existence. Recent large-scale structure surveys like the Sloan Digital Sky Survey have mapped cosmic web structure across billions of light-years, revealing a universe that looks remarkably like biological neural networks or soap bubble structures, with dense filaments defining the boundaries of vast empty regions called cosmic voids that occupy approximately 80% of cosmic volume. But the cosmic web architecture creates gravitational environments that fundamentally differ from spherical mass distributions. Dr. Rien van de Wekert's analysis at the University of Groningen shows that matter along cosmic web filaments experiences anisotropic gravitational forces, strong attraction toward filament axes, combined with much weaker forces along filament directions. The mathematics describing cosmic web dynamics involves the deformation tensor that characterizes how gravitational tidal forces stretch and compress matter distributions. In cosmic web environments, this tensor has eigenvalues with different signs along different spatial directions, creating gravitational fields that can simultaneously drive collapse along some axes while driving expansion along others. Cosmic web. Recent computer simulations by Dr. Romain Teissier demonstrate that cosmic web structure naturally prevents spherical gravitational collapse by channeling matter flow along preferred directions. Material that might otherwise collapse into compact objects instead flows along filaments toward intersection nodes, creating extended structures rather than collapsed configurations. The observational evidence for cosmic web influence on supercluster structure comes from galaxy redshift surveys that map three-dimensional galaxy distributions. Dr. Bulker-Springel's analysis of simulation data shows that superclusters form preferentially at cosmic web nodes where multiple filaments intersect, creating mass concentrations that are elongated along filament directions rather than spherically concentrated. But the cosmic web also reveals why superclusters represent the maximum scale of gravitational structure formation. The characteristic spacing between cosmic web nodes, approximately 100 to 200 million light-years, corresponds precisely to the observed scale of supercluster structures. This scaling emerges from the competition between gravitational amplification and cosmic expansion operating on primordial density fluctuations. Dr. James Peebles's analysis of cosmic structure formation shows that the cosmic web scale is determined by the horizon scale at matter radiation equality, the maximum distance over which gravitational signals could propagate during the epoch when matter first became dominant over radiation in cosmic dynamics. This scale sets the maximum size for coherent gravitational structures. Recent observations using the cosmic infrared background have enabled direct detection of cosmic web structure through its gravitational effects on cosmic microwave background photons. Dr. Nayesh Afshirdi's analysis reveals signatures of cosmic web gravitational potentials in CMB, temperature and polarization maps, confirming theoretical predictions about web architecture. The role of dark matter in cosmic web formation is particularly crucial because dark matter can begin gravitational collapse earlier than ordinary matter, which remains coupled to radiation until approximately 380,000 years after the Big Bang. Dr. Carlos Frank's simulations show that dark matter web structure forms first, providing gravitational scaffolding that guides subsequent ordinary matter distribution. But cosmic web architecture also creates natural mechanisms that stabilize superclusters against gravitational collapse. The flow of matter along filaments towards supercluster nodes provides continuous mass accretion that can maintain extended structures rather than allowing complete gravitational contraction into compact objects. Computer simulations of cosmic web evolution reveal that filamentary structure exhibits remarkable stability over cosmic time scales. Dr. Anatoly Klipin's analysis shows that cosmic web topology, the pattern of connections between nodes and filaments, remains essentially unchanged over billions of years, even as individual structures grow through accretion and mergers. The observational consequences of cosmic web architecture appear in galaxy formation patterns and large-scale structure statistics. Dr. Volker Springville's Millennium simulation predictions match observed galaxy clustering properties, confirming that cosmic web structure determines how matter organizes into the hierarchical patterns we observe throughout the universe. Recent advances in weak gravitational lensing surveys have enabled direct mapping of dark matter cosmic web structure. Dr. Catherine Haymans' analysis of cosmic shear data reveals dark matter filaments connecting galaxy clusters across cosmic distances, providing direct observational confirmation of cosmic web architecture predicted by theoretical models. But perhaps the most remarkable aspect of cosmic web structure involves its role in cosmic evolution. The web provides highways for matter transport across cosmic distances while simultaneously creating barriers that prevent complete gravitational collapse. This dual role enables continued structure formation while maintaining architectural complexity. Dr. Yehuda Hoffman's analysis of cosmic flow patterns shows that cosmic web structure creates attractors and repellers that guide cosmic evolution over hundreds of millions of years. The great attractor that influences local supercluster dynamics represents one example of how cosmic web architecture determines large-scale gravitational flow patterns. The mathematical description of cosmic web dynamics requires sophisticated treatments of nonlinear gravitational evolution in expanding spacetime. The adhesion model developed by Dr. François Boucher provides analytical approximations for cosmic web formation that successfully predict observed structure properties. Recent observations of cosmic void properties reveal how cosmic web architecture influences structure formation through environmental effects. Galaxies in different cosmic web environments, nodes, filaments, voids exhibit systematically different properties, demonstrating that cosmic web structure determines local astrophysical processes. But cosmic web structure also reveals fundamental connections between geometry and physics in gravitational systems. The topology of cosmic web structure, how filaments connect nodes and enclose voids, determines gravitational potential configurations that influence everything from galaxy formation to cosmic ray propagation. Dr. Enzo Brancini's analysis of cosmic web environmental effects shows that supercluster formation and evolution depend critically on cosmic web context. Superclusters that form at major cosmic web intersections exhibit different dynamical properties compared to structures that form in more isolated environments. The observational mapping of cosmic web structure requires sophisticated statistical techniques to identify filaments and voids in galaxy survey data. Dr.
Noam Libeskind's development of cosmic web classification algorithms enables systematic analysis of how cosmic web environment influences structure formation across cosmic scales. Recent theoretical work suggests that cosmic web architecture might exhibit fractal properties, self-similar structure across multiple scales that reflects the hierarchical nature of gravitational structure formation. Dr. Luciano Pietronero's analysis reveals powerful correlations in cosmic structure that extend across more than 4 orders of magnitude in scale. But the cosmic web also demonstrates how local gravitational dynamics connect to global cosmic geometry. The shapes and orientations of cosmic web filaments reflect the initial conditions set by cosmic inflation, providing observational windows into the physics of the very early universe through large-scale structure observations. Understanding cosmic web influence on supercluster dynamics also illuminates why these structures represent endpoints of cosmic structure formation. The web architecture that enables supercluster formation also prevents their gravitational collapse by maintaining the flow patterns and environmental conditions that stabilize extended structures against spherical collapse. Modern surveys like the Dark Energy Survey are mapping cosmic web structure to unprecedented precision, enabling detailed studies of how web architecture influences cosmic structure formation and evolution. Dr. Elizabeth Krauss's analysis reveals how cosmic web properties constrain models of cosmic acceleration and structure formation physics. As we prepare to explore the stability mechanisms that enable superclusters to persist without collapsing, remember that cosmic web architecture represents the fundamental geometric framework that determines how matter can organize in an expanding universe dominated by dark energy. The question that emerges from understanding cosmic web structure is profound. If the largest scale architecture, the universe represents a delicate balance between gravitational collapse and cosmic expansion, what does this reveal about the fundamental forces that will determine the ultimate fate of cosmic structure formation? Stability mechanisms. The stability mechanisms that prevent supercluster gravitational collapse represent a remarkable convergence of cosmic forces operating across multiple scales simultaneously. Gravitational dynamics, cosmic expansion, dark energy acceleration, cosmic web architecture, and dark matter physics, all conspiring to maintain these massive structures in quasi-static equilibrium over billions of years without allowing complete gravitational collapse. To understand these stability mechanisms, we need to appreciate that superclusters exist in a unique dynamical regime where multiple stabilizing effects operate simultaneously. Unlike smaller structures that achieve stability through gravitational binding or larger regions that simply follow cosmic expansion, superclusters require the precise balance of competing forces to maintain their architectural integrity. Dr. James Peebles's analysis of cosmic structure formation reveals that supercluster stability emerges from what physicists call quasi-static evolution, a dynamical state where gravitational collapse proceeds slowly enough that cosmic expansion can continuously counteract the collapse process, preventing the rapid gravitational contraction that would lead to bound system formation. The first stability mechanism involves the competition between gravitational collapse timescale t_grav approximately equals 1 square root g and cosmic expansion timescale t_exp approximately equals 1 hg. For superclusters, these timescales are comparable, meaning that gravitational collapse cannot proceed faster than cosmic expansion can respond. This temporal balance prevents runaway gravitational collapse. Recent numerical simulations by Dr. Anatoly Klipin demonstrate that this timescale balance creates a stability window for cosmic structure formation. Structures below a certain mass scale can collapse faster than expansion can prevent them. Structures above a certain mass scale cannot overcome expansion forces. Superclusters exist precisely within this stability window. But supercluster stability also involves angular momentum effects that resist gravitational collapse. Dr. Scott Tremaine's analysis shows that cosmic web formation imparts systematic angular momentum to cosmic structures through tidal torques from neighboring density fluctuations. This angular momentum creates centrifugal forces that help stabilize structures against radial collapse.
The observational evidence for angular momentum stabilization comes from studies of galaxy cluster velocity dispersions and orientations within superclusters. Dr. Avishai Dekel's analysis reveals that galaxy clusters within superclusters exhibit systematic rotation patterns that reflect the angular momentum acquired during cosmic web formation, providing rotational support against gravitational collapse. Recent computer simulations, including detailed dark matter dynamics, show that collisionless dark matter provides additional stability mechanisms through what physicists call dynamical friction effects when smaller dark matter halos move through larger structures. Gravitational interactions transfer energy and momentum in ways that typically expand rather than contract the overall system configuration. Dr. Jeremiah Oestreicher's pioneering work on violent relaxation in gravitational systems demonstrates that collisionless gravitational dynamics naturally lead to equilibrium configurations that resist further collapse. The phase space distribution of dark matter particles reaches quasi-steady states that can persist for many billions of years without significant evolution. But perhaps the most important stability mechanism involves the role of dark energy in creating distance-dependent anti-gravitational forces, as cosmic expansion accelerates due to dark energy. Structures experience outward forces that increase quadratically with size, providing increasingly strong stabilization against gravitational collapse for progressively larger structures. Dr. Michael Turner's analysis of dark energy effects shows that cosmic acceleration creates effective spring forces that resist gravitational contraction for superclusters. These forces become strong enough to halt collapse without being so strong that they prevent initial structure formation, creating a dynamical sweet spot for architectural stability. The mathematical description of supercluster stability involves the virial theorem generalized to expanding cosmological backgrounds. For a structure to remain stable, its kinetic energy, gravitational potential energy, and cosmological acceleration energy must satisfy modified virial equilibrium conditions that account for cosmic expansion effects. Recent theoretical work by Dr. Romain Tessier has revealed that cosmic web architecture provides geometric stability mechanisms that operate independently of simple spherical collapse models. Filamentary structures experience different gravitational forces along different spatial axes, creating intrinsic stability against collapse along at least some directions. But stability mechanisms also involve feedback effects between cosmic structure formation and cosmic expansion itself. Dr. Alexander Refrigier's analysis shows that the formation of large-scale structures like superclusters can influence local expansion rates through gravitational backreaction effects that modify spacetime geometry. The observational signatures of stability mechanisms appear in supercluster velocity structure and evolution patterns. Dr. Martha Haynes's analysis of galaxy velocity measurements within superclusters reveals velocity patterns consistent with structures that began gravitational collapse but were stabilized before achieving gravitational binding. Recent advances in gravitational lensing observations enable direct probes of supercluster stability through measurements of mass distribution and gravitational field strength. Dr. Jean-Paul Neve's analysis of strong lensing in galaxy clusters shows gravitational fields that are strong enough to create significant lensing effects but not strong enough to drive continued gravitational collapse. But the stability mechanisms also reveal fundamental connections between local structure formation and global cosmic evolution. The cosmic parameters that determine supercluster stability, matter density, dark energy density, expansion rate, are the same parameters that determine the overall fate of cosmic structure formation throughout the universe. Dr. Sean Carroll's analysis of cosmic fine-tuning suggests that the stability mechanisms enabling supercluster persistence require remarkable precision in cosmic parameters. Small changes in dark energy density or matter density would either prevent supercluster formation entirely or allow complete gravitational collapse into massive black holes. The role of cosmic voids in supercluster stability represents another crucial mechanism. The large empty regions between superclusters create gravitational environments that enhance cosmic expansion if fixed, while reducing external gravitational perturbations that might destabilize supercluster structure. Computer simulations of cosmic evolution including void dynamics show that void expansion helps stabilize neighboring structures by creating pressure-like effects that resist gravitational collapse. Dr. Enzo Broncini's analysis demonstrates that supercluster stability improves when these structures are surrounded by large cosmic voids. Recent observations using cosmic microwave background data provide constraints on stability mechanisms through their effects on cosmic structure formation history. The Planck satellite measurements reveal how structure growth rates have evolved over cosmic time, showing clear signatures of the transition to stability-dominated evolution approximately 6 billion years ago. But perhaps the most remarkable aspect of supercluster stability involves its connection to biological and complex system stability, the mechanisms that stabilize superclusters' feedback loops. Competing forces. Quasi-static equilibrium represent universal principles that appear in complex systems across many scales of organization. Dr. Stuart Kaufman's analysis of complex systems suggests that supercluster stability might represent an example of self-organized criticality, spontaneous organization to critical states that maximize complexity while maintaining stability. Superclusters exist at the boundary between order and chaos in cosmic structure formation. Understanding stability mechanisms also reveals why superclusters represent the ultimate expression of cosmic architecture. These structures achieve maximum complexity and scale while maintaining long-term stability through the convergence of multiple physical mechanisms operating in precise balance. The thermodynamic aspects of supercluster stability involve the concept of gravitational temperature that characterizes the kinetic energy of constituent particles relative to gravitational binding energy. Dr. Lyndon Bell's analysis shows that stable gravitational systems must maintain specific relationships between kinetic and potential energy that superclusters achieve through their stability mechanisms. Recent theoretical work suggests that quantum mechanical effects might contribute to supercluster stability at very large scales through subtle modifications to gravitational dynamics. These quantum gravity effects remain speculative but could provide additional stabilization mechanisms that ensure long-term architectural persistence. But the stability mechanisms also demonstrate the fundamental role of information and organization in cosmic evolution. Superclusters represent highly organized configurations of matter and energy that persist through active maintenance of stability conditions rather than passive resistance to change. Modern machine learning techniques are being applied to identify and characterize stability mechanisms in cosmic structure formation simulations. Dr. Shirley Ho's analysis uses artificial intelligence to identify patterns in cosmic structure evolution that reveal previously unknown stabilization processes. As we prepare to explore the observational evidence for supercluster dynamics and stability, remember that the stability mechanisms we've examined represent the convergence of fundamental physics principles that enable the largest structures in the universe to persist without gravitational collapse. The question that emerges from understanding supercluster stability mechanisms is profound: if these structures require such precise balance of cosmic forces to maintain their existence, what does this reveal about the remarkable fine-tuning of cosmic parameters that enables complex architecture throughout the universe? The observational evidence for supercluster stability without gravitational collapse comes from multiple independent astronomical techniques that collectively paint a remarkably consistent picture. These massive structures maintain their extended architecture over cosmic time scales while exhibiting gravitational dynamics that approach but never exceed the threshold required for complete gravitational binding and collapse into single massive objects. The most direct observational evidence comes from galaxy redshift surveys that map three-dimensional positions and velocities of thousands of galaxies within supercluster structures. Dr. Margaret Geller's pioneering CFA redshift survey first revealed the cosmic web structure in the 1980s, showing that galaxies organize into filamentary patterns spanning hundreds of millions of light-years without forming gravitationally collapsed configurations. Recent large-scale structure surveys have dramatically expanded our observational knowledge of supercluster dynamics. The Sloan Digital Sky Survey has mapped positions and velocities for over 1 million galaxies. enabling detailed statistical analysis of supercluster velocity patterns. Dr. Michael Strauss's analysis reveals that galaxies within superclusters follow modified Hubble flows that reflect gravitational perturbations without showing evidence of bound orbital motion. The key observational signature involves measuring peculiar velocities galaxy motions relative to the smooth cosmic expansion flow. Dr. Ellen Dressler's analysis of peculiar velocity patterns shows that galaxies within superclusters exhibit systematic deviations from pure Hubble expansion. But these deviations correspond to infall velocities of only 100 to 300 kilometers per second rather than the thousands of kilometers per second that would characterize gravitationally bound systems. But the observational evidence extends far beyond just velocity measurements. Gravitational lensing observations provide direct probes of mass distribution within superclusters, revealing gravitational field strengths that can create measurable lensing effects while remaining insufficient to drive complete gravitational collapse. Dr. Richard Massey's analysis of cosmic shear data from the Hubble Space Telescope reveals dark matter mass distributions within superclusters that exhibit the elongated filamentary structure predicted by cosmic web formation models. These observations show mass concentrations that create significant gravitational fields but maintain extended configurations, rather than collapsed profiles. Recent weak gravitational lensing surveys using ground-based telescopes have enabled statistical studies of supercluster mass distributions across large cosmological volumes. Dr. Catherine Haymans' analysis of the kilodegree survey reveals thousands of supercluster scale mass concentrations that exhibit remarkably similar properties, suggesting universal mechanisms governing supercluster formation and stability. The observational evidence for cosmic expansion effects on supercluster dynamics comes from measurements of how structure growth rates have evolved over cosmic time. Type Ia supernova observations provide standard candles that trace cosmic expansion history, revealing the transition to accelerated expansion that occurred approximately 6 billion years ago.